Hello everyone, this is Mr. Kennedy from geometry class. This is my first experiment with flipping a lesson. This lesson comes from chapter 12, section 4, all about spheres and their surface area and volume. So let's review what we know about spheres. Spheres, the definition is all the points a given distance from the center. So all the points that are the same exact distance from some central point, we call that point the center. And we can show that distance by using the radius. And the radius of a sphere can go up to the right, it can go straight down, it can go any direction. Because a sphere takes place in space. It's a three-dimensional solid object. So let's compare a sphere to a circle. They're both round, and often they're confusing because they're so similar. So a sphere is in 3 dimensions. So it's also in space. 3-dimensional space, whereas a circle is just in 2 dimensions. It's on a 2-dimensional plane. It's flat. It doesn't have anything other than just a flat surface. Finally, the whole point of this video, the whole point of this lesson is to determine if my ice cream cone melts on me, if I'm still going to be able to eat and enjoy everything that was in that scoop. So let's wait and find out. Okay, we're back. Now let's reconnect with what we already know that relates to spheres. Going back to circles. We already know about the circumference, and we know about the area of circles. Let's review those formulas. The circumference, or the perimeter of a circle, is given by the formula 2 pi r. Whereas the area of a circle, area has square units, so we're expecting to see some sort of squared variable. And in fact, that's what we get. The area is pi times r squared. Alright, so if we were given an example like, I've got a radius of a circle that's 6 feet, and I would like to know what the area, the surface area of that circle is. How do we find that out? We use the formula for the area of a circle, and we plug in our value of radius. Let's see what we get. Area equals pi r squared, and our r in this case, we're going to substitute it in 6. So pi times 6 squared. 6 squared is 6 times 6, which is 36. We get 36 pi, and the units of any area need to be squared. So we started with feet, we're going to continue with feet squared. So the area of that circle, 36 feet squared. Now, I want you to think about something. Let's say I made a sphere with the exact same radius. It had 6 feet. I made a huge sphere. Okay. If I took the area that we just found here, and I made, let's say, like a towel or some sort of piece of paper that I could cover that sphere with, how many circles would it take to cover the sphere with the same size radius? Think about that. Give yourself a couple seconds, say it out loud, and in the next slide, I'll reveal the answer. Alright. How many circles would it take to cover the sphere with the same radius? What did you guess? Well, the answer was, can you see that? 4. Exactly 4. Kind of cool. Alright, so the area of a circle is pi r squared. So if there are 4 of those, the surface area of a sphere must be 4 pi r squared, because it's our area of a circle times 4. That's all there is to it. Let's try an example with this. What if we had a sphere whose radius was 3 root 2, and we were asked to find the surface area? Let's use our formula. Surface area equals 4 pi r squared. In this case, that means 4 pi times 3 root 2 squared. So what's 3 root 2 squared? Well, that means 3 root 2 times 3 root 2. So that's 9 times 2, or 18. I'm getting 4 pi times 18. And 4 times 18 is 72. So we end up getting 72 pi, and this is surface area. So we must have some sort of unit squared, and I didn't specify what kind of units we were starting with in this problem. So we're just going to use generic U for units. what if we were given the surface area and we wanted to find the radius? Let's see one of those. Let's say the surface area of some sphere was 100 pi. Alright? Now, I want to find the radius. Find r. So I'm going to use the same formula. Surface area equals 4 pi r squared. Now I'm going to substitute in 100 pi for my surface area. And that still equals 4 pi r squared. Now we need to solve for r. Here we go. Let's divide pi out of both sides. And how about we divide by 4? That'll make those cancel. And this side will turn into 25 equals r squared. So to find r, we need to take the square root of both sides, leaving us with 5 equals r. So in this case, 5 units. Again, it didn't specify any kind of unit, so just generic units. And the radius is a linear term. It's a length, so it's just units, not units squared or units cubed. All right. There we go. We've begun our work with surface areas. On to volume now. All right, and now we're moving on to the volume of spheres. So the formula for the volume of any sphere is 4/3 times pi times the radius cubed. Now this is volume, so the units are going to be cubed, so it seems to make sense that the radius is also going to be cubed. If you're curious where that formula comes from, there's a section in your book that explains it, and I'm happy to help you find that and go through that in class. Basically, in a nutshell, it happens because when you take the volume of a cylinder and subtract the volume of two cones that have the same height, you end up getting the volume of a sphere. You don't need to go into that right now unless you're super curious, in which case open up your book, see what you can find. Section 12.4. Alright, let's see an example of how this volume formula can be put to use. So, what if I had a sphere with a radius of 3t? What would be my volume? Let's see. Volume equals 4/3 times pi r cubed, which means 4/3 times pi times 3t cubed. Now what is 3t cubed? That means 3t times 3t times 3t again. It's going to end up being 4/3 pi times 3 times 3 times 3 is 27, and t cubed is t to the 3rd power. Now let's simplify our answer here. We can divide out of 3, making this a 1 and this a 9. And finally, 4 times 9 will give me 36 pi times t squared. Now this is volume, so my units must also be squared. How about not squared. There you go. Mistakes happen all the time. Since it's volume, the units must be not squared, but cubed. 36 pi t to the 3rd, units cubed. Let's see another example where we start with the volume and you have to find the radius. So what if the volume was 500 pi over 3? I would like to know, what is the radius of that sphere? Let's use the same equation. So if I know the volume is 4/3 pi r cubed, I'm going to go ahead and write that. I'm going to say 4/3 pi r cubed, which is the volume, is equal to, well, the volume, 500 pi over 3. And now I just want to solve for r. First off, I'm going to multiply both sides by 3. Which cancels my 3 on the left and my 3 on the right. Next up, I'm going to divide pi out of both sides. Done, done. Now we're left with 4 pi r cubed. Ooh, nope. Made another mistake there. 4 r cubed equals 500. I am now going to divide by 4, and I'll get r cubed equals 125. Now, to undo r cubed and get back down to r, we need to take the what root? Not the square root in this case, but the cube root. Put a little 3 up at the top, that signifies the cube root. So you must ask yourself now, what number times itself again equals 125? Well, it's 5. And since this is a radius and it's a length, the units will just be u, generic units. Okay, now we've seen the surface area of spheres and we've seen the volume of spheres. Let's apply this to a very important ice cream scenario. Here we go. Okay, now we've made it to the important problem, the ice cream. Now let's assume it's a day like today. This is Friday. It's over 80 degrees in Petaluma, which is the first time it's happened in 2012. I was sweating all day, but it was fantastic. Perfect day. Perfect day for some kind of ice cream. Although I'm also vegan, so I don't eat any dairy. So in my case, I'm going to be going for a sorbet. And my favorite type of sorbet is blackberry, especially in the local area where we have so many blackberries. When they're in season and they're delicious, wow, you can't beat it. I usually go to a place in Fairfax called Fairfax Scoop. It's a tiny little closet of a store. They make everything by hand. It's all local ingredients, and most of the stuff's organic, which I really like. So here we go. Let's say it's a hot day, and I've ordered a scoop with a radius of 3 centimeters. Now the cone that it came in, the only cone that they offered, had a diameter of 5 centimeters and a height of 24 centimeters. If you think about that, that's a really skinny and long cone. Probably not the best, but hey, I'll take it. Now here's the question. If I, for some reason, didn't eat that scoop right away and it melted because it was so hot, would the cone have enough space, enough volume to hold my scoop? Let's assume I'm outside, I'm about to eat my ice cream or my sorbet, and I get a phone call. Bring, bring. Oh, hey, how's it going, Mr. Moquete? Yep, I'm making the video right now. Yep. Alright, talk to you later. Alright, maybe some minutes have passed there. That was a little abbreviated version, and I look down and my scoop has melted completely. Has it overflowed or is it inside the cone? Will I have to drink it? Yes. Will I drink all of it? I don't know. It depends if there's enough space. So let's see. We're going to need to compare the volume of the cone with the volume of the sphere, the scoop. Let's do a little competition here. The volume of the scoop equals 4/3 pi r cubed versus the volume of the cone. And if you recall from last time, the volume of a cone is 1/3 the area of its base, which is pi r squared, times the height. Okay. So let's calculate our volumes. The volume of the scoop itself is 4/3 times pi times r, which is 3 to the 3rd power. Now, 3 to the 3rd power is 3 times 3 times 3, which is 27. So we're going to get 4/3 pi, times 27. And when we reduce that, I can cancel my 3 and make this a 9, leaving me with 36 pi units cubed. We're dealing with volume, so this must be some sort of units cubed. And I think I specified the units, didn't I? They were centimeters, so let's get more specific. 36 pi centimeters cubed. Okay, let's compare that to the cone. So we get 1/3 pi times r squared. Again, what's the r of our cone? Well, the diameter was 5, and the diameter is 2 radii mixed together. So my radius must be 5/2. 5 divided by 2 squared times the height, which was given to us as 24. let's do some arithmetic. 1/3 pi, 5 halves squared is 5 halves times 5 halves, which would be the 25 over 4. Okay, I'm going to cancel a couple things where I can. Let's see, how about a 4, and I'll make this a 6. And then I can cancel a 3 and make this a 2. And I just am left with 2 times 25, or 50 pi. Now the units here must come back and be cubed, because we have volume. And as I learned earlier, it's centimeters, so centimeters cubed. Okay, so let's compare them. This is the competition. Is there enough space in that cone to hold the entire scoop? The cone has 50 pi, cubic centimeters. The scoop only takes up 36 pi. So, what happened? Did I get to drink all of that scoop? Yes, I did. Was there an ice cream crisis? Oh, I should have changed my answer here. Was there enough room? Yes. Was there a crisis? No crisis. That scoop was small enough that it fit inside the cone with room to spare. Alright, let's go on to a review, and then we'll... Alright, we made it, you guys. This is the last slide. It's just a summary. So in closing, when we're dealing with spheres, if we want to find the surface area, it's 4 times pi r squared. If we want to find the volume, it's 4/3 times pi r cubed. And in closing, I want to ask one more challenge question. Here's the question. Why are most planets spherical? How come planets tend to be spheres? Why aren't they cubes? Why aren't they triangular prisms? Why aren't they, I don't know, hexagons or soccer balls? I don't know. Why are they spheres? Think about that and be ready to give me an answer when you get back to class. Thank you so much for watching this video. I hope it wasn't too long. The first version was like 23 minutes, so this one's shorter. I'm doing my best. Hopefully it'll get better in the future. Have a great weekend. See you in class. Bye-bye. Bye-bye.